Completing the square is a topic where you can get pretty good at it, but without really understanding what you're doing. That leaves you vulnerable to a tricky question. So the purpose of this video is to help you understand why we complete the square and why it actually works. Okay, so why do we complete the square? Well, in my view, the reason why we complete the square is because we want to take something that has a double appearance of x, and so this has a double appearance of x, there's physically two appearances of x, and we change it so that there's a single appearance of x. So this becomes this. Now that's what completing the square is for. The squaring business, that's not important. The main thing is that two appearances of x become one appearance of x. Now completing the square is not the only way of doing that. So for example, older girls become quite good at turning that into, I think, this. That's the same thing. Double appearance of x, now there's a single appearance. Year 7 students, they hopefully know, before they start doing any red dudes on that equation, that it's much simpler to collect like terms, because then a double appearance of x will become a single appearance. Now the reason why we do that is because it can be easier to solve equations if we know what x to look at. It can be much easier to graph stuff if there's a single x, because the algebra we're looking at has a closer connection to something very basic like this. I claim that that's much easier to graph than that. So that's why we complete the square. It's to take two appearances of x and change it to one appearance. That means that you would never be asked to complete the square on that, because, or even on this, because there's only one appearance of x. The square is already completed on that. So that's why we complete the square. Next thing is, why does it work? Okay, well, I'm just going to have a very brief discussion of all the ways in which we know, when we're working in maths, that we are just changing the look of something, not its fundamental meaning. So here's just a little bit of a list. When we collect like terms, we've always known that we're just changing the look of it, not the actual meaning. When we multiply top and bottom of a fraction by something, or when we divide top and bottom of a fraction by something, which is often done by cancelling, then we know we're just changing the look of it, not its fundamental meaning. We know that under some circumstances we can write, instead of one symbol, we know that we can write two, and we know that we're not changing the fundamental meaning. And of course we know that if we have an equation, it's very easy to change radically the look of something without changing its meaning, because we can do red dudes. So every time we do a red dude on this, we change its look to become simpler and simpler, but we don't change what it actually means. Now some red dudes are dangerous in that respect. This is clearly false, but if we square both sides, we get something true. So that's why squaring both sides is regarded as a dangerous red dude. It's because it does change the meaning. That is clearly false, but when we square both sides, we get something true. So this last minute has just been a bit of a walkthrough of the various ways in maths that we know we can change the way something looks without changing what it means. We've got collection like terms, cancelling, this business with the square roots, red dudes. We've got ratios, can times both sides of a ratio by the same thing, etc., etc. Now that leads me to completing the square, the mechanics of it. Okay, now I'm going to do a couple of examples at once. I'm going to do y equals 2x squared plus 3x I don't know, plus let's not say 3x, let's say 8x plus 4. I'm going to have also let's say 3x plus 5x, and I'm also going to have 3x squared plus let's say 12x plus 12 equals 0. Okay. Now, no matter what your teacher's method, I bet you anything, it is much simpler to understand, and we can be much safer, we can be much more confident that we're using it safely if the coefficient of x squared is 1. So in each of my examples, the coefficient of x squared is not 1. But the way we handle it is different. Okay, this is the simplest one. We can handle that just by dividing everything by 3. That's a very safe red dude. We can be confident that these mean the same thing. Whatever's a solution to this is also a solution to that. Whatever's a solution to that is also a solution to that. And now we have that hidden one there, which makes almost every teachers in the world method pretty easy to work. Now, this one also has an equals sign. We can do a red dude to get rid of that too. We just have to be aware that that will cause a y divided by 2. Okay? This doesn't have an equals sign, therefore we cannot do a red dude on it. Okay? So if we want to get rid of that 3, we have to do something highly artificial. We have to basically create the most enormous bracket and kick in the method entirely within those brackets, very patiently copying down the 3, copying down the left bracket, copying down the right bracket. Now, this is very much against the grain because you only ever take out a common factor in year 7 and 8 when you can see a common factor. But here we do it anyway because it's required to make the method work. Okay? Now, I think about completing the square as hating what's in third position. So I bump out what's in third position. I just move it slightly along. This one has already got a blank in third position, so there's no need for me to hate anything or move anything there. And this I've created a space there as well. Okay. Now, what would I like to be in third position there? Well, there's a very famous little trick. You halve this and then you square it. There's two ways to halve a fraction. One is to halve the numerator. That's not pretty for us because that's odd. The other way is to double the denominator. Half of 5 over 3 is 5 over 6. You then square that and you get 25 over 36. And that is what I wish was in third position. So this is wishful thinking. I'm now going to put it there. What do I wish was in third position here? Halve the 4 and then square it. Half of 4 is 2. Square that, you get 4. So that's wishful thinking, me just putting it in there. And same thing over here. Although in this case, it turns out that I already had what I wished was in third position. So let's not do anything strange there. Let's just leave that there. Okay? There's no point doing anything artificial if what you wish was in third position is already in third position. Okay? Now, I mentioned that I had wishful thinking. Okay? I just inserted that there because I wished it was there, and I inserted that there because I wished it was there. You cannot just randomly put stuff in because you feel like it. You have to make sure that you are just changing the look and not changing the meaning. And on this sheet, I showed you a whole bunch of ways that we have of being sure that we're changing the look but not changing the meaning. Okay? And all of them are great except for this squaring both sides business. Okay? Which is a complication that you probably don't need to worry about for a while. Okay? So what method have I got here to avoid the accusation that I've changed the question? Well, there's an equals sign. So I can introduce that 4 by adding it to both sides as a red dude. And now nobody can say that I changed the question. If you compare this to this, this has got a 4 on both sides, but because it's on both sides, it's fine. What about this one? I randomly introduced a 25 over 36 there. Somebody might say, you can't just put that there, it's going to change the value. It's going to change the value by, quite a lot. Not just the 25 over 36, but also by 3 times the 25 over 36. So how can I avoid that accusation? Well, it's a very simple little fix. Just immediately subtract exactly what you put in third position. You don't care because that amendment is in fourth position and you don't care about fourth position. It's third position that you are caring about. But now if anyone says you changed the question, you can say, yeah, I changed the look, but all you did was add effectively a 0, which doesn't make any difference. Okay, and in this question, remember, we didn't have to do anything at all. Okay, now once you have put something in third position that you prefer, you now factorize it. And that trick of halving and then squaring the coefficient of x is designed to ensure that you get the same bracket twice. Remember, you're just factorizing the triple. Everything else needs to be copied down. The 4 is copied down. The y over 2 is copied down. The 2 is copied down. This one, what did I have at the halving stage? I had 5 over 6. And the reason why that's the business, and the reason why completing the square is a clever method, is because when you factorize to get a repeated bracket, you need only write it once with a little squared symbol, and that is the point. The point is to get to a position where you only need to write x once. And there we go, that x is now written once. So that's the purpose of it. And in all 3 of my examples, completing the square is now done. Okay. Now this one looks just like an algebraic game, just a question in an exam to enable you to strut your stuff. This is just algebra on a page. There's no equal sign. There's nothing you'd have to graph, nothing you'd have to solve. So in most exams, that would be the finishing point. In this one, it looks like you might have to graph it. Graphing is way easier than graphing tends to be easier when y is by itself. So let's get y by itself. Let's first of all subtract 4 from both sides. That doesn't wreck anything. We've still got a single appearance of x. Now we're going to double both sides. And now we're good. We've got y by itself with various machinery that you learn over the course of year 10, 11 and 12. You can graph that. What about this? That's something you'd probably have to solve. You solve it by a red dude, square root both sides, and then take away 2 from both sides. So let's just be clear. That's just an algebraic game. The moment you see the single appearance of x, you're done. That's probably a graphing question where you get y by itself and then do your thing. This is probably just a solution question where you get x by itself by doing red dudes. Now in each case, it's way easier if there's a single appearance of x to look at, and that is what completing the square is for. Let's just review my 3 examples. Why did I do 3 examples at once? I wanted to demonstrate that you've got more room to move when there's an equals sign, because you can do red dudes. You can do the same thing to both sides. This one is especially convenient because you could get rid of this 3, just dividing everything by 3, and nothing is easier to divide by a 3 than a 0 because it just stays as a 0. I couldn't do red dudes on this one, that's why I had to do this mega bracket that stayed there right until the very end. See? Bracket, 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 bracket. When new bracket came, they were inside the old brackets. I wanted this example so that you would understand that when you divide both sides by 2, it causes all sweetness and light here. It does cause a temporary complication there. I also wanted to have an example where we didn't have to do anything because what we wished was in third position already was in third position. So therefore, you don't have to do anything to both sides. You don't have to do any of this crazy adjustment. And finally, I definitely wanted to have an example to show how sometimes you can introduce your desired third term with a red dude. So there's the 4 and there's the 4, which weren't there in the line above. Whereas sometimes you have to introduce it by putting it in there and then immediately subtracting it. All 3 of these are fine. Now some teachers entirely like to use that, some teachers entirely like to use that, and some teachers entirely like to use that. But I guess the warning to you is do not get too stuck in that groove, because the methods that are best for each of them may not work on the others. So that's the purpose of this video.